So far in StatMech, what have we done? We looked at the three ensembles. We really covered the part one of our course, which is the three ensembles and setting up the probabilities in those and how to manipulate them and play with them. Okay, so now we are moving into the second part, which is applications to non-interacting systems. And even this can be quite rich. You can derive a lot of interesting things by applying what we have done so far to systems where you assume that particles don't talk to each other, they are independent. Even then you can get very interesting results. Later in part 3, we will look at interacting systems, which of course the math gets a bit messier. You have to make approximations, but it's a nice language of how to do things. And part 4 will be some more advanced topics, a little bit of renormalization group, a little bit of this and that. We will see when we get there. Part 2 will take us a bit of time as we work through it. We will be going over it until end of March or beginning of April. And whatever we are doing today is included, might be included on the midterm. What we do Thursday won't be included. Okay. So today, what are we going to do? We are going to look at these, not just non-interacting, but non-interacting ideal systems, really, really simple things. And yet we can get a lot of mileage out of this. As we go further, you will also need to brush up your quantum mechanics. For some of the applications we are going to do next, if you are not comfortable with quantum mechanics, it will seem very, very strange. And if you're comfortable, it will seem less strange. So the things that you need to know from quantum mechanics, I don't think we will read it today, but if just go back tonight or tomorrow, read it. So we will be using it in the class on Thursday. So the first thing you need to know is what is particle in a box, how to solve that, what are the energy eigenvalues, what are the wave functions, things like that. Just time independent Schrodinger equation, okay? Nothing time related. The second thing you should look up is the quantum harmonic oscillator. What are the energy eigenvalues of quantum harmonic oscillators? We don't really care too much about the wave function, but we do care very much about the energy eigenvalues, things like this. And it would be useful if you brush up your uncertainty principle. That always helps. And it would also be useful if you brush up your Pauli exclusion principle. So these are topics which are covered in PChem 2. Okay, this is PChem level stuff. So you might have forgotten it, but you have done it in your undergrad if you have met the prerequisites for this course. Otherwise, go look up Khan Academy videos. They tend to do a good job of covering all this. Okay, so we will be needing this. So as we start further, as we go from here, let's take a moment to think about why did we give partition function the name partition function? Why do we call it partition function? So, and again, to remind you, what do I mean by partition function? I have the canonical ensemble partition function, which is going to every microstate and doing e to the power minus beta e nu. I have the grand canonical partition function, which is going to every microstate, doing e to the power minus beta e nu minus mu n nu. So the reason we give it the name partition function is, imagine that if your system was made up of two composite independent systems. So the energy in a microstate, E nu, is coming from E nu 1 plus E nu 2. If your system is broken into two parts, then in such a case, if you write down the partition function, what will it become? It will become Q is equal to summation mu e to the power minus beta e nu, which is summation. Now I have to sum up over the microstates of system 1, microstates of system 2, or double summation, e to the power minus beta e nu 1 plus e nu 2. And now we notice that, well, nu 1 only affects this exponential and nu 2 only affects this exponential. So we can write it in a separate form. We can write Q is equal to summation nu 1 e to the power minus beta e nu 1 multiplied by summation nu 2 e to the power minus beta e nu 2. Okay, so the partition function of the composite system 1, 2 is the same as the partition function of system 1 multiplied by system 2. So it's a product. That's the idea. It partitions into this type of thing. And of course, the product makes sense. Why? Because thermodynamics comes from partition function by taking a log of the partition function, right? If partition function, you would say, oh, what's special about product? If Q12 was Q1 plus Q2, you would still be telling me it's a partition function. It partitions into a sum of two things. But you would have a problem. Thermodynamics won't work. Log of Q12 is not log of Q1 plus log of Q2. The thermodynamics won't be extensive, right? We need thermodynamic state functions to be extensive. In your first homework, in the state functions, a few of you forgot n. So I deducted a few points. I've been very, very lenient in gradings. In grading, you'll see, like super, super lenient. I won't be like that in the midterm, I promise. I made the midterm on Sunday. It's great. We'll have a lot of fun. There is one bonus problem, and otherwise there's a bunch of problems. So now if you have n atoms that are, or particles, independent of each other, then the partition function for this n atom system is going to be q1 to the power n, right? In the second homework, there was a problem where you did something like that. Remember, the answer was 1 plus 2e to the power minus beta epsilon plus something else. Some of you forgot to take to the power n. You were asked the partition function for the n particle system. And that's where this thing about, this is very, it's important to say here, mention here that I'm talking about indistinguishable particles, okay? Or let's not go into that difference here. Sorry, let's leave it as it is. I want to talk about indistinguishable particles starting from here. So now let's say we have n indistinguishable particles where each particle can take energy epsilon 1, epsilon 2, epsilon infinity, any of these values. This is sort of similar to the problem we did in class earlier. Remember, there we had n particles, and each particle could be in ground state or excited state, right? There were not infinite values of energy. There were two values of energy, 0 and epsilon. There was another difference there. The particles were distinguishable. So remember how we wrote down the microstate there? We went to particle 1, and we saw whether it was 0 or 1. We went to particle 2, we saw it was 0 or 2. And then we had a long binary number, which read 0, 1, 1, 0, 0, 0, 1, 1, 1, something like that. We cannot do that over here because the particles are indistinguishable. So 0, 1, 1, let's imagine you had only two energy values here, epsilon 1 and epsilon 2, 0 and epsilon. If the particles are indistinguishable, then 0, 1 is the same as 1, 0. These two microstates are not different, right? So we have to write the microstate carefully here. So in this case, we will write down the microstate in the following form. We will write down it as a number, as a vector again, where the numbers are n1, n2, dot, 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 till infinity, n infinity, depending on how many energies do you have. And this says number of particles with energy epsilon 1. This says number of particles with energy epsilon 2. So if the particles are indistinguishable, this is what we need to do, okay? In such a case, if I asked you, what is the number of particles, total number of particles in a given microstate, what would that be? I need you to think about this. Fatime, what do you think? How will it connect to the small n's? It's easy if you think. If you have n1 particles in epsilon and energy epsilon 1, you have n2 particles in epsilon 2. Let's say there were only two types of energy, epsilon 1 and epsilon 2. and 5 of them were in epsilon 1 and 10 of them were in epsilon 2, then how many particles do we have total? 15. So in this case, how much should it be? How did you get 15? You got 15 by doing 5 plus 10. Now you have n1, n2, n to infinity. So what will be the number for expression for n nu? No, the sum. You added last time, right? You did 5 plus 10, correct? So this will be n1 plus n2 plus n infinity, because the particles have, every particle has to be in some energy, right? So it's going to come from somewhere. So if you think about it, it's obvious. Okay, Atli, now you tell me. Huh? What?
The summation of i's with the
Yeah, that's what I wrote down, right? So this will be summation I is equal to 1 to infinity ni. My question for you, Atli, is how about the energy in that microstate? How much will that be? So 1 second. So we had n nu is equal to summation I is equal to 1 to infinity ni. And now I'm asking E nu. How much will this be? N1 particles with energy epsilon 1. So how much energy are those N1 particles contributing total? N1 multiplied by epsilon 1.
Yeah.
So this will be Ni epsilon I is equal to 1 to infinity. Okay?
Nice.
It's very simple. And if you look at it, it will make sense where it comes from. Okay? But if I ask you, then it's like, wait, I don't know. So what are we doing here? We are looking at energy level epsilon 1, and we are saying we have N1 particles in this energy level. We are looking at energy level epsilon 2. We are saying, okay, we have N2 particles in this energy level, dot, right? And we are going to energy level epsilon infinity, and we have infinity particles in this energy level, okay? So, and this is to be contrasted from the case where we did our distinguishable particles, right? There we did not do that. There we looked at whether a particle was a particle-centered view. Now we have an energy-centered view. And the microstate here will be given by this number, n1, n2, dot, infinity. So now we can have this, even though we are talking about infinitely many energy eigenvalues, and when you look at the quantum harmonic oscillator or even simple harmonic oscillator, there is no limit on the energy values you can take. It can keep going up and up and up and up and up, right? There is, the spectrum just keeps going. It's the probability drops down with Boltzmann. But if you remember, omega of E keeps increasing with energy, while e to the power minus beta epsilon E drops down, right? So energies can be infinitely many. This does not mean that the number of particles has to be infinite, right? The number of particles might vary. Sometimes we will study particles where it is infinite, that is photons. Photons can get produced at will, so there is no problem. But for photons are fake, they just get produced. Here, have a photon. So if n was fixed, then we would have 0 less than equal to n1 less than equal to n, dot, 0 less than equal to n infinity less than equal to n, and the sum of n1 till infinity will have to be equal to capital N, right? So you're seeing we are moving towards a combinatorial problem before we know it. So these numbers that you use to describe the microstate, n1, n2, and infinity, are called occupation numbers. It's how many particles are occupying any energy eigenvalue, okay? And turns out that particles, and by particles I mean fake particles also. For example, phonon. Phonon is a fake particle. It does not exist. But you nod your head, I would say electron is a fake particle. Have you ever really held an electron in your hand? It's a wave, right? I mean, it's all quantization. If you really think about it, when we do our chemistry, we think, oh, electron makes sense. And you hear about phonon, you're like, that one I'm a bit not so sure. But you think about it, phonon is more intuitive than electron. And we will be studying everything in the next few weeks. We'll be studying phonon, photon, electron. We will be doing StatMech of all three. And we will see some very interesting results. So it turns out that most particles or matter, that's why I'm using the word particle loosely. I'm not just talking about the particle model of standard physics or quarks or things like that. I'm talking about anything that you want to describe ends up falling in one of two categories. The first category is known as fermions. In case of fermions, any Ni can take only two values. It can be only 0 or 1. This comes from Pauli exclusion principle. In the case, and the second one is bosons, where Ni can take any value from 0 or 1 or 2 up till infinity. There is no limit. Okay? Particles that fermions are said to follow Fermi-Dirac statistics, and bosons are said to follow Bose-Einstein statistics. And Bose is from India. He's from Samyak state, from West Bengal. It's not Bose like Jose, okay? It's Bose. You're from, why did I assume you're from West Bengal? I'm tired. Oh, must be tired. I'm so sorry. You're from New Delhi, right? No, but you did your schooling in New Delhi. This is strange. My neurons are entangled. I apologize. Every year I have some Bengali students in my class. That's why I assume. So I make this joke, I went into automatic mode. In fact, I have had Bose in the class in the past. So it's not Bose, it's Bose. So, yeah. So we will be studying these two types of particles. And it turns out you don't need to worry about things where you don't have particles where Ni can be 0, 1, 2, or 3. These are the two classes in which things fall, which is kind of amazing. Okay, and we will be studying them in detail. Any questions about this? So we will be, the way we proceed from here, we will be studying sort of in an abstract way, the thermodynamics of Fermi-Dirac and Bose-Einstein statistics. Before we do that, I want to give you some practical examples. And the math will be gnarly even in the practical examples, but it will give you hopefully a sense of why StatMech is so powerful. And the first thing that we are going to study now is phonons, or heat capacity due to atomic vibrations. So in early 1900s or late 1890s, or even before then, people were able to measure the heat capacity, Cv or Cp, as a function of temperature. Okay? And they found that for almost everything, it behaved that in the following way. As temperature went to 0, heat capacity went to 0. As the temperature raised, the heat capacity rose, and then it sort of became flat at very, very high temperature. So for almost anything, this heat capacity would take the value of 3 times R, the gas constant, Rydberg's constant, at very, very high temperature. And as T tends to 0, Cv tends to 0. In fact, people were able to fit this low temperature behavior. And they saw that Cv can be fit to a very high accuracy with the following expression, AT plus BTQ. So what we are going to study in the coming few lectures is the origin of this AT and BTQ. Okay? And turns out classical mechanics cannot explain this. In classical mechanics, if the world was classical, the heat capacity should not go to 0 as temperature goes to 0. This is a subtle point that I want everyone to appreciate. Why is it that you need quantum mechanics to have a heat capacity that goes to 0 at 0 temperature? This was one of the first triumphs of quantum mechanics, that it could explain things like this. This is what gave a lot of people motivation. And together, it was a triumph of quantum statistical mechanics. So why is it that classical mechanics, or a classical picture of reality, will always give Cv more than 0 as T tends to 0? Go ahead.
More so the CVs change, so you just kind of like the old V change, you can't have it be constant.
So yeah, you're on the right direction. So let's think about it more carefully. So what does heat capacity come from? And let's forget about electrons for right now. Okay, let's assume these are things where there is no like F electrons and things like that. Okay, deeply buried F electrons. Electrons are kind of useless. They are crap. If it's only atoms, and you pump heat into something. If I pump heat into this cup of coffee, Ami, what happens to the atoms? What is the origin of heat capacity? They start moving. And if it's a small amount of heat, you can say they move around. If coffee is not it's a liquid, it's not a crystal, but in a crystal, they would move around some equilibrium position, right? They would oscillate more and more along that equilibrium position. In classical mechanics, and listen to this carefully, in classical mechanics, when you plot the energy of moving around the equilibrium position versus R, the potential energy curve is going to look something like this. Here, I just drew a harmonic curve. In reality, it will be some complicated curve. But the point is, all oscillations are allowed in classical mechanics, right? The tiniest movement is also allowed. Quantum mechanics is funky. Quantum mechanics says the only oscillation that is allowed is the one that takes me to the first eigenvalue, first excited state. The other excitation that is allowed is that takes me to the second excitation state. So in other words, in quantum mechanics, if the energy that you give to the system is less than h cut omega, it will be like, I don't know what to do with this. It's like me giving you half a penny. What will you do with it? Money is quantized at 1 penny, right? I cannot just give you half a penny and be like, go, enjoy, have a blast, right? Even with 1 penny, you won't be able to do anything. But that's my point. You can maybe do something. If you collected many pennies, you will have something going, you will have a party. So in quantum mechanics, if energy is less than h cut omega, the heat is useless. In classical mechanics, even h cut omega by 100 is sufficient to do something to the system. So the system is so hungry for heat that it has a capacity for heat, right? Anytime you give it some heat, it will be like, sure, let's raise our temperature. Let's oscillate a little bit more. While quantum mechanics, you give it energy smaller than h cut omega, it will be like, I really don't know what to do with this. You need to give me more, okay? And it will be trapped. So you need to, in classical mechanics, this cannot go to zero. You will always have a non-zero heat capacity, even at low temperature, okay? So what we are going to do next is to understand, first we will show that what does classical mechanics do then? It gives you a boring answer, and especially if you assume a classical harmonic oscillator, where we are going to assume a simple case where our atoms are just moving close to equilibrium, okay, which is okay for small perturbations. You will find that classical mechanics, in fact, gives you a constant heat capacity equal to 3R. It's really boring. It does not work. Then Einstein and Debye both came into the picture. They both used quantum mechanics. Specifically, they used quantum statistical mechanics, and we will work through that. Einstein was a bit lazy. You will see why he was lazy. His heat capacity dropped down very quickly. His heat capacity went down exponentially as the temperature went to zero. Debye got it right. Debye's heat capacity, we will derive in class, goes exactly as TQ. But this all comes from movement of atoms. When you give heat to a system in metals, it's not just the atoms only that move, electrons can also move, right? So if it's an insulator, BT cube is sufficient. But if you have a metal, then electrons also start moving faster and faster, right? And electrons have their own issues. If they are close to the Fermi surface, they are going to move. If they are very far from the Fermi surface, they are like, I don't know what to do with this energy, right? So later we will see how electrons lead to AT type term. And the reason why we call this phonon is because when atoms move, when atoms vibrate, you can map them into some sort of quantization, right? And we will work through a little bit of that. So phonons basically, and if you want to get a better feeling for phonons, I recommend reading a solid state physics book by Kittel, for example. It will give you some initial. Just go look up Wikipedia and things like that. So phonons represent. So what is electron? Electrons is a quantization of charge, right? The minimum charge you can have is 1 electron. You cannot have half an electron. What does that mean? I don't know what that means. Similarly, in lattice vibration also, even in classical mechanics, there is a minimum amount of vibration, roughly speaking, when you look at the modes and things like that. So that's what's rough. So phonons correspond to atomic quantized atomic vibration in a lattice. And I want to use the word quantized carefully, it has actually nothing to do with quantum mechanics, and yet you get those type of movements. Okay, so if quantized confuses you, you can ignore that. It's just capturing how much atomic movement you have. So we are now going to study how to get this BTQ. How can StatMech come and explain this problem? So first, to do this, we will start with classical mechanics. In classical mechanics, and we will find that it does not do a good job. So let's work through it. And it's also useful, this derivation, because you work through the steps of calculating the partition function and actually getting the Helmholtz free energy from it, and then getting the heat capacity. So this is a typical problem that you will be working with. So what we are going to assume here, that our insulator is made up of n independent atoms. Each atom is oscillating around some equilibrium position. So what we are going to derive won't work if our solid melts and becomes a liquid, right? Then that's not true, because now the atoms are diffusing back and forth. And even in a solid, you do have diffusion, which is complicated. So for now, we are just assuming that we have these nice, well-behaved atoms on some sort of lattice. Here I drew a simple cubic lattice, but it could be anything. And each one of them is just moving in some, it can move in any direction, right? Along its equilibrium position. So if I now think about the distance this atom has moved from its equilibrium position, there will be a potential, there will be a ripple, there will be a penalty. It cannot go too far, right? It's like come back, come back, come back, so it has to come back. So we can write down the potential energy of a given atom as a function of the displacement r, or the distance r it has moved from its equilibrium position, okay? So this will be given by some U naught, which is the crystal energy of the system, the binding energy that is keeping the crystal stable, some constant. This is some binding energy. Plus, we can do a Taylor series along, because we are doing small perturbations, right? So we'll look at partial U by partial R multiplied by R plus partial U double derivative multiplied by R square half and more terms. What can we say about this term close to equilibrium? Huh? 0. Why?
Which are a minimum.
That's your answer, right? What is the derivative of U close to R? And even if your true potential energy is very complicated, close to minimum, it's going to be 0. If it's not 0, then you're perturbing in too far. Make smaller perturbations, right? So this is going to be approximately 0 close to equilibrium. Okay, we are talking, and for small oscillations. Cool. So what do we have now? We have, and the higher order terms we will ignore. Terms like r cube, r to the power 4, things like that, because r is very small, so r to the power 3 is going to be very, very small, things like that. So we don't care about that. So U of r will be approximately U naught plus half double derivative of U with respect to r square multiplied by r square. So if you are not working with spherical coordinates, you are working in Cartesian coordinates. Anyone knows what is the name of such double derivative? Ami, you should know maybe. Aren't you working with Hongzhou?
Yeah.
What's the name of this thing? A lot of who here has done TFT ever? So you should know what this is. It's the Hessian. So codes like, when you calculate phonons in codes like Gaussian, this is the matrix it computes. Once you have this, you can, through the machinery we are doing, you can go back and compute everything about phonons. So this is Hessian, but for now, it's just a number. And remember, the potential energy of a system does not depend on temperature. It's kind of obvious statement if you think about it, but then you might get confused also. Free energy depends on temperature, right? Free energy is U minus Ts. But U itself is not a temperature dependent thing. U is what it is, right? So this thing, double derivative of U by double derivative of R squared, does not depend on temperature, which is why you can use zero temperature TFT codes to calculate it. If it depended on temperature, you wouldn't be able to do density functional theory and get it, right? It just wouldn't work. So this is a temperature independent value, which we are going to call alpha. Okay. It's the curvature of the potential energy close to the minimum. And of course, alpha itself might depend on what exact value of R you have, but let's just look at some sort of curvature that you have. Okay, roughly how much is the curvature? So this means that U of R can be written approximately as U naught plus alpha by 2 R square. Okay. So this is our harmonic crystal, and we are interested in understanding what is the heat capacity of this harmonic crystal. So as you all proceed in your PhD, maybe some of you will have this bad idea of inviting me to be on your PhD qualifying exam or candidacy or something like that. And the question I'm going to ask you next is a question I'm going to ask you there. I ask two questions a lot. And if I don't get an answer to those two questions, especially from students who have taught, I become very sad. The first question is, why is CP more than CV? Without using math. And all of you did in the first homework, oh, we have to do work against the atmosphere. You wait till your qualifying exams, you will all forget it. So if you're going to have me, you better remember that. The second one is, for a harmonic crystal, we are going to calculate the heat capacity, but let's think about something else, which is the thermal expansion coefficient. As you pump heat into a crystal, things are moving, right? And they will be moving. We know things expand, generally speaking, except water between 0 and 4 degrees Celsius. What is the thermal expansion coefficient of a harmonic crystal where all atoms are moving as per this harmonic oscillator? Any ideas? This is the picture, right? So we assume for all of this a harmonic crystal. And you don't have to think about quantum or classical. The answer is 0. A system made up of harmonic springs will not have thermal expansion. Why? The movement is symmetric. Sometimes it goes in this direction, sometimes it goes in that direction. It will be fluctuating more, but on an average, it will be at the same spot. So in this crystal, for which we are going to calculate heat capacity, is actually kind of useless because it won't even expand with heat. It will just stay at the same thing, right? So you need to have some unharmonicity. You need to have a potential energy that looks something like this. And that's a Lennard-Jones potential, for example, which we'll study later, where it's not symmetric about origin, okay? It goes to the other side. So, and this is also a good practice problem for you, and maybe I will give it on the midterm, maybe not. Maybe I'll give it on the final. Do this. So intuitively, it makes sense. It's going to be on the origin. But try to calculate this mathematically for a system made up of harmonic oscillators. You can do it now, because you can calculate the partition function. From partition function, you can calculate thermodynamics. So you have to think, how do I get the thermal expansion coefficient from a QNVT ensemble made up of classical harmonic oscillators, CHO. Okay, work through this and see how to connect. If you crack it without looking up on the internet, you will feel proud of yourself. That's all I can say. Okay, so, and it turns out to be 0, and that's what I want you to prove. Okay, good. But now let's come back to heat capacity. So we have U of R, potential energy, is equal to U naught plus half alpha R square. But that's not the only thing that the atoms have when you give heat to them. They also have kinetic energy, right? They are also moving. You have to account for the kinetic energy. Kinetic energy will depend on the momentum of the particles, right? Kinetic energy does not depend on a harmonic oscillator for R. I mean, invariably it does in an indirect sense, but kinetic energy is really momentum squared by 2m, right? E squared by 2m. So kinetic energy will be, so this first, let's write down this thing explicitly. So U naught plus alpha by 2 x squared plus y squared plus z squared We are talking about distance r from the origin. So that was spherical coordinates. Now we switch to Cartesian coordinates. So x square plus y square plus z square. And Kp will be 1 by 2m momentum along x square, y square, z square. So notice we have immediately switched to phase space. Now we are thinking about x, y, z, px, py, pz. We immediately switched whenever it's convenient, we do whatever we want, okay? Now, the problem is, it's not just this energy. This is one particle. We have n particles in the system, all of them. So the whole thing will become super complicated, right? It will be u naught multiplied by n plus alpha by 2 x1 squared plus y1 squared plus z1 squared plus alpha by 2 x2 squared plus y2 squared plus z2 squared, so on and so forth, right? It will be a horrible integral. But now notice our n atoms are independent. They are not talking to each other, okay? Therefore, the n particle partition function is q1 to the power n, right? If we can calculate the partition function for one particle, which follows this potential energy and kinetic energy, we just need to take to the power n. And if you want to be careful, you have to divide by 1 over n factorial because the atoms are indistinguishable and things like that. Let's not worry about that one for now. Okay, so my notes have my equations numbered, so maybe I should be nice and number them. Okay, good. So this one I have as equation 4. Let's go back. This one is equation 3. This one is equation 2. And I suppose this is equation 1. Okay. So now let's calculate Q1, the partition function for one particle. We will work in canonical ensemble. So we go to every microstate, nu, and calculate e to the power minus beta E nu. What does microstate mean for one particle? Microstate, remember the first time we did microstate, we studied that microstate tells you where in phase space you are, right? So where in phase space can this particle be? It can be somewhere along XYZ, right? It can be somewhere along PX, PY, PZ. So microstate is really, where is this particle in this 6-dimensional space? Then we will have to think about uncertainty principle, because when we think of this 6-dimensional space, we have a minimum limit, minimum size resolution, which comes from Planck's constant, right? So that's how we are going to calculate it. So what I'm going to do next is going to seem very bizarre, but become familiar with this operation. I'm going to change this summation into an integral. Because what am I doing here? I'm going to every microstate and calculating e to the power minus beta E nu for that microstate, right? So instead of doing that, I can write this down as a 6-dimensional integral, where the first 3 are going over P, the next 3 are going over R, okay? And for each of them, I calculate e to the power minus beta E nu. What is e to the power minus beta E nu? E to the power minus beta E nu is energy as a function of momentum and position in that point of phase space divided by kT. And now this will be multiplied. It's an integral, so dqp, dq bar. And due to uncertainty principle, I need to divide this by 2 pi h cut whole cube. Okay, so this is Q1. So take a moment, stare at this. We just switched from a discrete summation, which would be useful in a quantum mechanical setup, to an integral, which is useful in a classical setup. Everyone okay with this? Huh? It will take some.
What is the constant outside there?
This thing is Planck's constant. I could have written h, but we like to be fancy, so we write it 2 pi h cut. Okay. Let's call this equation 5. Q1 is equal to this thing. Put equation 2 and 3 in 5. Why? Because E here is U of R plus K of P. So this energy, this Hamiltonian of the system is separable. The kinetic energy and the potential energy are sum of two things. In physics, often there are systems, especially magnetic systems, where things are not separable. You will have things like R dot P, and then you're screwed. You cannot do what we are going to do next. So even though this looks like a horrible 6-dimensional integral teaser, it's very simple. It turns out to be a product of 6 Gaussians. And Gaussians can be done analytically, which is kind of amazing.
Sorry, what is that term that's directly inside of the integral bracket?
This thing, EXP,
Oh,
otherwise known as 2.71828. It's crazy, right? That 1828 repeats twice in the first 10 digits. I don't know why. I don't think there is a reason. So we put equation 2 and 3 and 5. What does that mean? I put down the value of E. Okay, I put down the value of U. I put down the value of K. What does that become? That gives us Q1 is equal to, first we have a constant, right? U naught. U naught can come outside. U naught does not depend on R or T. So this will become e to the power minus U naught by KT divided by 2 pi h cut whole cube integral Px integral Py integral Pz integral x integral y integral z e to the power minus beta alpha x square by 2 e to the power minus beta alpha y square by 2 e to the power minus beta alpha z square by 2 multiplied by e to the power minus px square beta by 2m e to the power minus py square beta by 2m, and I will stop for a moment after writing this, don't worry. E to the power minus pz square beta by 2m multiplied by dpx dpy dpz dx dy dz. This is the full 6-dimensional integral limits, beauty or ugliness, whatever you want to call it. Write down the whole thing, it's worth it. Is the integral in x, what is the range of x? Minus infinity to plus infinity, right? We said, okay, it can be small oscillation, but nope, we are going to integrate minus infinity from infinity. Why? Because the exponential will take care of it, right? So if you integrate this thing, minus infinity, okay, is everyone done writing this horrible thing? Julia, you done? Julia is furious. This 2 integrals, in fact, these 3 integrals, they are the same thing. It's just a switch of variables. It's like saying, integrate cosine of x from -1 to 1, or integrate cosine of y from -1 to 1. Is that different? So when I was like in 11th grade or something, or some point, I would do things like this. My grandmother would be like, do a lot of math, and I would just make up like fake math problems and change it. Like, look, so many math. But it was all the same, right? So these are the same integrals. All you have done is to change x to y to z. Of course, if you had a box where x was different from y, then the problem would be different, right? But right now we don't have that. Furthermore, if you stare at it a little bit more, it's not just x, y, and z that go from minus infinity to infinity. The momentum also goes from minus infinity to plus infinity. Huh? Oh no. I've deducted 2 points in one of your homeworks.
Okay.
You did not staple. If you use a clip, I deduct 2 points.
Wait, no.
Yeah. Yeah. Yeah.
It was like 20.
No, you used a paper clip. Fatime also in one of the homeworks. So you lose 2 points. It's a
Oh,
total. The reason being that when I wake up at 5 a.m. to grade your homework, it's like paper everywhere, and then Pakoda comes and starts rolling in it. So please staple next time, okay? And also for the Slack homeworks, I have deducted lots of 2 points from lots of you, because you just submitted file 687 HW2, and you have not written your name. So I have to go back to Slack and check, do handwriting, and all handwriting. Half of you have very good handwriting, half of you have terrible handwriting, like me. I'm the terrible handwriting category. So I've deducted 2 points for that also. When you submit by Slack, don't just name your file. Please put your name on top of the document, okay? So I know what it is. 2 points is well within noise. It doesn't matter. It's like, so some of you have scored 98 on 100 for that reason. So Px goes from minus infinity to plus infinity. Py goes from minus infinity to plus infinity, right? It's momentum, it's not speed. Momentum has a direction, right? So if you think about it, e to the power minus, we all already agreed that the x integral, y integral, z integral is the same thing. It's just the variable is different. Now, if you think about it, minus beta alpha x square by 2, the position integral, and minus beta by 2m px square, these are also very similar integrals. Instead of x, now you have px. And the thing that is different is that here you have minus beta alpha by 2, and here you have beta by 2m. Alpha does not show up in the momentum part, right? Because alpha was related to the curvature of the potential area. But all 6 are Gaussian integrals. We can do all of them in the same one stroke of pencil. And what we are going to use, so let me write it down. All 6 are Gaussian integrals. And for Gaussian integrals, minus infinity to plus infinity, e to the power minus x square by 2 sigma square dx is equal to square root of 2 pi sigma square, right? This is the expression for Gaussian integral that you can look up anywhere. So we are going to use this. Let's call this horrible integral as equation number 6. Let's call this Gaussian expression as 7. Okay, so for the x, y, and z, sigma is the same. For the px, py, and pz, sigma is the same, but it's different from the sigma for x, y, z. Vivian, you happy with this? Okay, sure? Okay. And then one of the problems, some of you forgot about the molecules lying flat on the surface. So you forgot to multiply by 2 to the power n in the partition function, because it's not just the excited molecules, it's also the down molecules, right? Some of you have entropy going to 0 at high temperature. That's not good. But a lot of you got the heat capacity curve correct, that it had a transition. And I appreciate that you even provided your notebook and things like that. In your final exam, you won't have access to anything like that, but in the midterm, you can use any tool you want. Okay. So let's use all this. Let's use 7 in 6, the values of the Gaussian, and it just, all 6 integrals give you this square root of 2 pi sigma square, okay? That's all you get. And you get that Q1 is equal to e to the power minus u naught pi kt divided by 2 pi h cut whole cube. For the momentum, you get mkt, square root of mkt cube. Each momentum gives you square root of mkt. And each position gives you square root of kt by alpha cube. Okay? This is what we get by using equation 7 in 6. If this is confusing, just go back home and it will take 1 minute to do this part.
So when we assume that the integrals are independent, we are assuming that the x values can be taken independently of the px values.
Yeah.
But that's not true.
It is, because the Hamiltonian is separable. The energy of the system is u of x plus k of p. So the probability of observing the system in a certain energy is equal to e to the power minus beta u multiplied by e to the power minus beta k. It's a product of these two things. It is exactly independent. If it was not separable, if you had terms which were jointly dependent on x and p, as it happens in magnetic fields and things like that, then this won't work. Okay? So this is how phase space works, right? You might say the reason why you're getting confused is like a harmonic oscillator, right? You would think, well, on a swing, like when you're on a swing and you go to the top of the swing, your speed becomes 0, right? And you come to the bottom of the swing, your speed is very high. So it looks like, well, the speed depends on where I am. But I'm not talking about the value of the speed, I'm talking about the variable. These two variables are separate. They are independent of each other, okay? And this is due to this Hamiltonian. For any time you have on the swing, the u of x is half kx squared, and potential energy is what it is, right? So you don't have terms that couple x and p. They happen in physics, they happen in relativity, and they happen in magnetic systems, but not here. Any more questions? Okay, so this makes Q1 equal to 1 by 2 pi h cut whole cube mk to the power 3 by 2 k by alpha to the power 3 by 2. I'm basically getting rid of all the non-temperature terms, okay, because that's what I seek eventually, to the power 3 by 2 multiplied by e to the power minus u naught over kt multiplied by t cube. So all of this is temperature independent, okay? It's some grand term which does not depend on temperature. It's very grand, let's call it G. G multiplied by, and I want to keep my K for some reason. I want to hold on with the Boltzmann constant. So I will get G multiplied by KT to the power cube multiplied by e to the power minus u naught by KT. This is my single particle partition function. It's sort of interesting, right? It's like a Boltzmann factor multiplied by some cube. The cube type thing is already showing up, but it does not help us. We don't get the cubic heat capacity just from this, unfortunately. And where G is T independent constant. Let's call this equation 8. Okay, now it's thermotime. Okay, one step before thermotime. This was single particle partition function, right? What I really needed is the n particle partition function. So let's write that down. So Q of n is going to be Q1 to the power n. That's going to be G to the power n, KT to the power 3n, e to the power minus n u naught by KT. Let's call this equation 9. Now it's thermotime. And let's just call this Q for the full system, okay? I need the heat capacity. And what I have is the partition function for a canonical ensemble. How do I go from Q to heat capacity? If this was on your final and you did not have your notes, what would you do? Tucker, what do you think? Of what? L and Q, that right direction. And what is L and Q for canonical ensemble? The Helmholtz free energy, right? So he's in the right direction. He's like, well, I don't know what quite to do, so I'm just gonna flap my legs and arms, differentiate a bunch of things, and maybe something will work out. That's kind of correct, because thermo, that beautiful subject, tells us that entropy is minus partial A by partial T at constant V. Where did that come from? 684. So if you don't remember your thermo, you're done. You keep differentiating, you won't get to the right answer. Where does this come from? How would I derive this if I was lost? Anytime you're lost in thermo, go to the integrated first and second law. If you go to the integrated first and second law, you will see this happens in 2 lines. But I do not recommend doing that all the time, especially on the final exam. Maxwell relations, what is the expression, what corresponds to first derivative of state function when something is held constant? These things should be on your cheat sheet, so you can quickly look it up, okay? So you would find that, and why does this relation matter? Because A is what we get for canonical partition function. A is the thermodynamics brother of canonical partition function, and we know entropy is this. Well, we didn't need entropy though, we needed heat capacity. So one more relation remains. How do I get heat capacity from entropy? CV is partial Q by partial T, right? So CV is T partial S by partial T at constant V. Okay. So CV is double derivative of Helmholtz free energy. So let's work through this now. we will first calculate our A from equation 9, then we will calculate S, and then we will calculate CV. And you will find that CV comes out to be 3nK. It's a constant, it does not depend on temperature. I will pause for a moment. Okay, I can move next page. Okay, no one objected. So A is equal to minus KT ln of Q. So minus KT G to the power n, KT to the power 3n, e to the power minus n u naught by KT. This is equal to minus nkt log G, and sometimes I write ln, sometimes I write log. It's always natural log. Okay, I don't, in this course, if in a homework or exam I need you to take log with respect to 2 or 10, I will specify the base. Unless specified, the base is always natural log. Minus nkt log G minus 3 nkt log KT and minus KT multiplied by minus n u naught by KT. So this one does not depend on temperature, the third term. And what am I going to do next? I'm going to get entropy. I'm going to differentiate A with respect to T and get the entropy, right? So this term won't matter. This term will give something linear. For the heat capacity, let's just work through it carefully. So S is equal to minus partial A by partial T at constant V. What's that going to be? That's going to be nk log G. And here we will have to do product rule, right? Because both have temperature. So plus nk log G plus 3 nkt multiplied by 1 kt plus 3 nk log kt. Kt cancel. What are we left with? We are left with S is equal to nk log G plus 3n plus 3nk log kt. And what is CV? CV is T partial S by partial T at constant V. This one does not have any temperature term. This one does not have any temperature term. This is the only thing that has temperature term, right? What does that give us? T multiplied by partial S by partial T. 3nk multiplied by 1 over T. Log K does not matter because it's log K plus log T. So when you differentiate the log K, it just goes to 0. T cancel, and we get what I told you we will get, that heat capacity for classical harmonic oscillator is independent of temperature. In chemistry, there is a name for this law. Anyone remembers? This is known as the Dulong-Petit law. Okay, people had measured this, that at high temperatures, insulators or most things start to behave as simple. They didn't even know atoms were there. They had just measured that the heat capacity tends to become constant as you get to very, very high temperature. And we just saw that indeed, if you assume that if a system is made up of atoms which are classical and oscillating in every direction. So Samyak, the question you asked earlier is, why is X independent of Px? To me, that is not the harder part. The harder part is X is independent of Y. In a crystal, that's not going to be true normally, but we are even assuming that here, like the directions are independent of each other. So we are not just assuming X independent of Px, we are also assuming X independent of Y, independent of Z, and things like that, okay? So, and we get we get this picture, and like I said, in the beginning of the class today, in a classical picture, even if you did not have a harmonic oscillator, you had something else, you can always pump in some energy over here to excite the system and get a heat capacity in the classical picture. In the quantum picture, you have ground state and then you have discrete energy values. So if your energy is smaller than this h cut omega, it's useless. Nothing is going to happen. So next time we will do the same harmonic oscillator, but in the quantum setup. We will use a quantum harmonic oscillator. So please go brush up the energy eigenvalues. Quantum harmonic oscillators also have wave functions. We are not going to use the wave function. You don't need to brush up your Hermite polynomials and things like that, or your ladder operators or anything funky. Just the energy eigenvalue, what it is. And then we will work with that. And we will see how Einstein was lazy, but Debye got it right. So next class will be here. Next class will be slightly shorter. I will finish in 45 minutes because I have to go organize a workshop at 1 p.m. in Rockville. So it's going to be so I will finish in 45 minutes for sure. And then I have a flight to Switzerland at night. And then next Tuesday's class will be on Zoom. Okay. If you don't have any place to attend Zoom from, come here, bring headphones and just attend the class on your laptop over here. Okay. If you have some place else, you can do that. And next Tuesday, right after class, the midterm will be released. You will have 72 hours plus change. Friday, 4 p.m. or whatever it's written on the midterm, it will be due by Slack or in my office over there. And then you can have a wonderful spring break. Okay.